Welcome to the lecture today. We don't dive into concepts of photogrammetry or robotics here today, but we want to look a little bit into some mathematical tools that we are frequently using, especially if we think about 3D reconstruction tasks. So the lecture here today is just a short reminder of a few things you should know, for example, from your linear algebra courses or your basic math courses. But I just want to revisit them so that you can check if you still know what's going on or if you may spend some extra time revisiting some of the concepts here. So again, math is a tool that we are really using here frequently, and the idea of this lecture is not to go into the details, provide you with proofs or providing detailed explanation why things are in a certain way. I really just want to repeat some facts, and so if those facts are not clear to you, it may be a good point in time to revisit some of the concepts here. So this is a very brief, informal, sloppy, incomplete, unordered set of explanations or recipes that we may want to use. So again, treat this only as a thing you should be aware of A, B, C, D, E, and if not, go back to your textbooks and study this, because at that point in time, you should know things. So what are we going to cover here? Often we are faced with the problem of solving a system of linear equation, so a system of the form ax equals b, for example. And depending on how A looks like, there are different ways how you can do that. If the system is, has an exact solution, or it's overdetermined or underdetermined, these are things that you need to take into account. Then we are looking into so-called homogeneous systems. So this is ax equals to 0. How does x look like in order to fulfill the equation ax equals 0? And singular value decomposition will play a role in here. We will briefly look into least squares, how to solve a least squares problem. For example, using Gauss-Newton. Again, very high level, not going very much into the details, just as a reminder to repeat certain things so that later on in the course we can actually use those techniques as tools in order to solve certain problems. Skew-symmetric matrices will pop up in here. These are matrices where the negative of the matrix is transposed, and so this has some applications especially in 3D that are kind of useful for us, and this will also, there will be relation to rotation matrices or approximations of rotation matrices that we will be taken into account. There's a longer part on homogeneous coordinates. This is something you probably haven't heard yet, and I decided to make a small own lecture on that, introducing homogeneous coordinates and what we can do with them, because that's a concept that is very handy in photogrammetry and computer vision in order to express certain mathematical expressions in a much simpler and easier way, and this simplifies a lot of transformations that we need to do and things like this. So this will not be covered here in this lecture today, but the rest we will briefly go over those topics over here. Okay, so let's start. Ax equals b. Solving a system of linear equations. So we have the form A is a matrix, x is a vector, b is a vector, and we want to know how x should look like so that A times x is equal to b. And in order to solve ax equals b, there are certain things that we need to take into account. So basically 3 cases. The first case is that A is a square matrix, so same number of rows and same number of columns, and it has full rank. So this is kind of the case which typically leads us to an exact solution if it exists. Then we can have an overdetermined systems or an underdetermined system. We can see this as having more constraints than variables or a smaller number of constraints than variables. And so as a result of this, there may be no solution at all, but maybe we want to compute an approximate solution, or there are multiple solutions out there. And depending on which case we are in, there are different ways how we can actually approach the problem. So we start with kind of the standard case. This is the case that you typically have seen in school already. You have ax equals b, a system of linear equations, and you want to solve this. A is a square matrix, has full rank, and this is kind of, so to say, the best case solution, because in this case there is a unique solution. So there is one vector x which actually solves this problem, and obtaining this vector x can be achieved in multiple different ways. So there's not just one solution how you can do that. There are multiple ways how you can do that. Some are easier to do, some are computationally more efficient, some are specially designed for large-scale systems or exploit different properties. And so the way you choose the technique. Which way you choose it depends on your application and on your capabilities of whatever, implementing it yourself or using a matrix library which does this, or even automatically figures out what's the best approach to do that. So a few things on how you can actually solve that. So Gauss elimination is probably the technique that you learned in school to solve a system of linear equations. That's one way you can do this. Another thing you could do, you could invert the matrix A and then multiply it from the left-hand side. So you would have A inverse A, X equals A inverse B, and A inverse A is identity matrix. So as a result of this, we have X equals A inverse times B, and you solved it with respect to X. That may be okay for small matrices. If you have larger matrices here, this can become computationally costly. Therefore, what you can do is you can exploit the Cholesky decomposition. As an alternative way, again very briefly, the Cholesky decomposition of A basically decomposes A into two matrices, L and L transposed. So A is a product L transposed, where L is a lower triangular matrix L. And if this is the case, then we can actually write AX equals B as L transposed AX equals to B. And then we can actually break it down into solving two system of linear equations. So if you think L transposed X equals B, we can kind of combine this L transposed X into an own variable, say L transposed X equals Y. So we just introduce kind of this new variable Y, and then plug Y in here and say Ly equals B. So the only thing I need to do is I need to now solve two system of linear equations. Again, matrix times vector equals vector, matrix times vector equals vector. The only difference in here is that now those two matrices are lower triangular matrices, which I, as a result of this, can solve very efficiently. And so it may make sense to decompose the Cholesky decomposition and then solve those two systems. This can also become very useful in case your matrix A is sparse. That means a lot of the entries in this matrix are zero, because then there are even tools such as sparse Cholesky decomposition, which allows you to solve that in a more efficient manner, as it is shown over here. There are other ways like QR decomposition or conjugate gradients for large systems. So there are different ways how you can solve this AX equals B case if A has full rank and is a square matrix. So in the case we get an exact solution out, or maybe we don't find a solution, but if it's solvable, then we have an exact or a unique solution. It should be more a unique solution, so there's no ambiguity in here. And that's kind of the standard case, the thing that you'd probably have done in school. Okay, reality, however, is not always that great. So often we have an overdetermined system. And this is the case in most real-world situations. So for example, we have more observations about our unknown parameters than parameters. And if we don't have absolutely perfect observation, if there's noise involved, then this typically leads to a setup where we have more equations, constraints, so to say, on the variables than free parameters. And as a result of this, there exists typically no solution or no exact solution. The result was our measurements are affected by noise, so there is no single explanation that explains every observation perfectly. And as a result of this, whenever we deal with real-world data, we are basically ending up in this setup, unless we have exactly the number of observations than parameters. But most of the time, we have more observations. If we can't find an exact solution, we want to find a solution, an approximate solution. And we're typically looking into not saying AX equals B, but we basically move B on the other side. So AX minus B should be equal to 0. And then saying, okay, we can't bring that to 0, but we want to minimize the norm. So we want to bring this AX minus B as close as possible to 0, because it's kind of the best approximation that we can find for AX equals B. So instead of solving AX equals B, we are interested in minimizing AX minus B. So our solution that we typically end up with is this one over here, solving the system. And this is basically an ordinary least squares approach that we are taking over here. And if you go through this, the solution can be obtained for these types of setup so that X is A transposed A, invert this, A transposed B, and this gives you the solution for X. Again, the way you solve your least squares problem, there are different ways how you can actually do that, but this is the way for minimizing this equation in the standard form. Okay, the other thing that could be that we have more parameters than observation equations, for example. In this case, we have an underdetermined system. That means we are not able to figure out the solution. There are actually many solutions. So there are infinitively many solutions because I'm basically having a solution space. Of course, we can still have the situation that some of the equations, observations we have are inconsistent, then we even don't find a solution at all. But otherwise, assuming this is not the case, we end up with a solution space and we have enough, we have an infinitely large number of possible solutions. And that basically means we don't have enough information to actually solve the system. So we don't have enough observations, for example, for determining all the parameters. If we anyway want to find the solution which satisfies this, what we can do is we want to find an x which solves ax equals b, and typically we impose an additional constraint that is an x which minimizes the norm of x as an additional constraint. And if we go for this approach, then actually the solution is actually similar to the one we shown in the previous slide, except that the A transpose doesn't sit in here, but sits here in the front. And this is a way how you can actually solve ax equals b if A is an undetermined system, obtaining a solution for x, the one that actually minimizes the norm of the vector x and still fulfills this equation over here. Okay, that's so far what I wanted to explain you about linear systems, at least of the form ax equals b. There's a special case, and this is if b equals to 0. And this is something which we call a homogeneous system, so a system of the form ax equals to 0. And that is something that will actually pop up quite frequently in the courses or lectures that I'm teaching here. So we need this, for example, in the context of the direct linear transform, which is a mapping of cameras, how points are mapped from the 3D world to the 2D image plane, determining the relevant parameters involves solving such a system. Or camera calibration can be done in a way that I need to solve a homogeneous system. Or alternatively, this pops up for computing something which is called the fundamental matrix or the essential matrix. So basically estimating the orientation of a camera pair, whereas camera 1 with respect to camera 2, for example, involves solving such a system. So solving a homogeneous system is something that pops up multiple times in this course. So it's good to know about that, how we can do this in an efficient manner. Okay, so what we're interested in is actually not finding a solution for ax equals 0, because we can do this with the so-called trivial solution, simply setting x to 0, then of course ax equals 0 holds. Typically we are interested in finding the non-trivial solution, so a vector which is not the 0 vector that fulfills ax equals to 0. And so this basically means that we have an underdetermined system over here, and there's something which is called the null space of x, also written as of a, the null of a. And this null space contains all vectors x, so that ax equals 0 is fulfilled, and then all those x form the element of this null space. And you can see that this is not just one vector, these are multiple vectors which can do this, because we can simply scale up x by a factor of 2 or 3 or 4 or 5, and this equation still holds all the time. So what we have here is this matrix A has a so-called rank deficiency, so a reduced rank, and the amount of the rank deficiency, so how far the rank of A is away from a full rank matrix, is the dimensionality of this null space. So if you, for example, have whatever a 5 by 5 matrix A, and it has rank 3, and we have 5 minus 3 equals 2, so the null space would be a 2-dimensional space containing all those vectors that lead to ax equals to 0, and of course also all linear combinations of those vectors as well. So in the end we have the dimensionality of this matrix A. For a squared matrix here, it is the dimensionality of the null space equals to the rank of the matrix. So this is basically the rank deficiency that we have. This is the rank of A and the dimensionality of my squared matrix. So the question that we now have, if we have a matrix here which fulfills this, which has this rank deficiency, what is actually the impact on the eigenvalues of my matrix A? This may be a question that you may be interested in. So if your matrix A has a rank deficiency, that means there are some eigenvalues that are actually 0. And the number of eigenvalues that are 0 is exactly this rank deficiency, the dimensionality of that null space. This tells you how many eigenvalues are 0. So if we have an eigenvector, we now want to look into the eigenvectors that correspond to the eigenvalues that go to 0. So for any eigenvector, nu, we have a times nu equals a scalar here called lambda times nu. So this is a matrix and this is just a scalar. And this is the property that holds for the eigenvector and its corresponding eigenvalue. So this would be the eigenvalue for the corresponding eigenvector. If we now say we have an eigenvector or an eigenvector that belongs to this null space, so an eigenvalue of 0, then of course this lambda here would be 0. So a times v equals 0 times v, which must be 0. So a times v equals to 0. And that means that the eigenvector that corresponds to an eigenvalue of 0 is a solution to these to ax equals 0, and this holds for all combinations of those eigenvectors which corresponds to eigenvalues which are 0, and that means these eigenvectors actually span up your null space. So the null space of A, so all the possible vectors lie in there which bring ax equals to 0 or any combination of those vectors in here. Okay, so this is about eigenvectors, something you probably still remember, and there's another concept called singular vectors and not only eigenvectors. And the eigenvectors and the singular vectors and eigenvalues and singular values are actually related with each other. And so you can actually see that the singular values and vectors are a generalization of the eigenvectors and eigenvalues in the sense that the eigenvalues are only defined for square matrices which are real and so taking real numbers and symmetric and has non-negative eigenvalues. And the singular values and vectors can be computed for any other matrix. But if we are in this setup that we have a square real symmetric matrix with non-negative eigenvalues, then the singular values and the eigenvalues are actually the same. So the eigenvectors are not defined for non-square matrices, but the singular vectors are. So you can see the singular vectors as a kind of generalization of this. And as a result, we are using the singular value decomposition, actually a technique that allows us to compute those singular vectors and singular values very often when we are going to solve our system ax equals to 0, so homogeneous system. So let's briefly illustrate what SVD, or the singular value decomposition, is actually doing. So what the singular value decomposition, also called SVD, does, it basically takes a matrix A as an input and decomposes it into 3 matrices: a matrix U, a matrix D, and a matrix V, so that U times D times V transposed gives me exactly my matrix A. So I'm basically taking my matrix A and breaking this matrix up into 3 different matrices. So my matrix A is an m times n matrix, can be written as a matrix U, which is of dimension m times m, matrix D of dimension m times n, and a matrix V with an n times n matrix, so that U times D times V transposed gives me my original matrix A. And those matrices U, D, and V have special properties, and these are properties that we can actually exploit. So this matrix D, for example, here is a matrix which contains only of zeros except of this diagonal here. So if this matrix would be a square matrix, which is the case if A is a square matrix, it would be a squared diagonal matrix. Otherwise, we have the diagonal sitting over here. And this diagonal contains all the singular values of my matrix A. And again, if we are in the case of a square matrix, real values only in there, symmetric, and the eigenvalues are larger than 0, then the singular values actually correspond to our eigenvalues over here. So this is the special matrix D, which has this diagonal form. In addition to this, this matrix U and this matrix V are orthogonal matrices, so similar as we know it from rotation matrices or reflection matrices, realizing reflections. These are the properties of my matrix U and my matrix V over here. And the important thing, what we're interested in this matrix V or V transposed, is that it stores the singular vectors corresponding to the singular values which are stored in D. So D contains the singular values, and V or V transposed corresponds to the singular vectors. So if it's V transposed, it's here a row corresponds to a singular vector. If we look into V and not V transposed, of course, this matrix gets transposed, and then these are the individual rows. So if we just use V, then of course I will need to take the row. And here you need to be a bit careful depending on the method library that you're using. Often they return V and not V transposed. So and then you need to look to the last column, or to the column and not to a row of this matrix that you get returned from your library. So just make sure you're not mixing up V and V transposed. So the important thing is, in here is what I forgot to mention, is on the diagonal, we typically have the singular values ordered according to their size, starting with the largest one up to the smallest one. And they're all positive, so the smallest value that they can actually take is 0. So there may be some of them which are 0 over here. And that means if you have the singular value which is 0, you have the corresponding singular vector which corresponds to the singular value which is 0. And if they're ordered by size, I simply can jump into the last position, and then this last singular value corresponds to this small singular vector, and so this corresponds to the one which brings my system to 0 if the diagonal element here is 0 as well. So what I need to do is I basically need to inspect the smallest element of D, the smallest singular value of D, see is it 0? If it is 0, then I can pick the last column of V, and then this is my solution because I found or extracted the singular vector that corresponds to the singular value of 0. So the key thing, if I want to solve AX equals to 0, I'm computing the SVD, I'm checking the position D and N, and if D and N is 0, I found a solution, and then the last column of V gives me a solution, a non-trivial solution for AX equals to 0. Non-trivial means the vector is not of length 0. Okay? So this is even interesting if you have a singular value which is non-zero. So if D and N is unequal to 0, even this is an interesting case, because they are ordered according to size, the singular values in this matrix D. So the singular value the singular vector corresponding to the smallest singular value, which is still larger than 0, is the vector that minimizes AX, or the norm of X, under the constraint that it has of length 1. So it's basically, if I can't find an exact solution, AX equals to 0, because again, we may have more observations than parameters we want to solve, then this is helpful because this is a vector which minimizes AX. If I can't solve AX equals 0, I'm often interested in kind of minimizing AX. And this is a solution to that minimizes AX under the constraint that X is of length 1. Of course, if I would kind of relax this constraint, of course, I could make that X as small as possible, and then this expression also gets smaller and smaller and smaller. Okay, so as a result of this, whenever we are confronted with an homogeneous system, SVD is your friend. So you can execute SVD, and out of the results of the SVD, you can directly extract the singular vectors, and these are typically the quantities you are interested in. And again, it's not necessarily the case that this only holds for one singular value. You can have multiple singular values which are 0. Then all the singular vectors would be a solution, or even the linear combinations of those vectors would be a solution to AX equals to 0. So there may be multiple solutions out there. And this, again, directly related to the null space of your matrix A. Okay, so that was all about solving linear systems. The next thing we want to look into is actually a least squares approach. And I'm not taking here a very formal geodetic approach, so therefore I called it a non-geodetic view on the least square things. Again, just a repetition very briefly on least squares so that you know what least squares is and what we can actually do with the least squares approach. And for that, I already prepared a 5 minutes video, so it's easy for me now because I can just hand you over to this 5-minute video and let you enjoy an explanation of least squares in 5 minutes that I recorded half a year ago. So welcome back to another episode of 5 Minutes with Cyrill. I want to talk today about the least squares approach. So what is least squares and what can we do with it? So least squares is a technique which allows us to infer parameters or states based on observations that we have. So it is a technique for state estimation and it is a very popular one. It has been developed by Carl Friedrich Gauss around 1795, known as die Methode der kleinsten Quadrate, and had its first showcase in 1801 when Gauss was able to predict the orbits of the planet Ceres very accurately, better than anyone else was able to do it, and this made the least squares approach popular. It was also used in the 1820s in order to measure the Kingdom of Hanover and in order to estimate point locations in the environment based on observations. So what you need to do in order to use a least squares approach is you need to be able to map your parameters or your unknowns or your states into what I call predicted observations using a so-called observation function. So you have a function f which takes as input the state, so your parameters, and it should generate predicted observations. So what should you observe given those parameters would be the correct ones? And what you then do is you compare those predicted observations with the actual observations that you have obtained. And then you try to vary the parameters of that observation function so that the predicted observations are as close as possible to the actual observation that we obtained. So that you then generate parameters which are in line with the actual observations that we have obtained. And the error that we are minimizing is the sum of the squares of those errors. And that has led to the name least squares because we are minimizing the sum of the squares of the errors consisting of the discrepancy between what we are expected to observe and what we actually observed. And is used for a large number of problems starting from mapping, localization, SLAM, camera calibration, bundle adjustment, and a large number of other problems. So what we, however, assume in the least squares approach, at least in its basic form, is a linear dependency between the parameters that we have and those predicted observations. And if there is no such linear dependencies, we actually need to linearize our problem in order to solve it using the technique that Gauss has proposed. So how do we linearize a problem? And in the real world, we always have to linearize because the majority of our problems are nonlinear. So we need to compute Jacobians used in a Taylor expansion in order to linearize our problem and then solve this approximative linearized problem in the end. For that, we need to build up a so-called A matrix, which is built up based on the Jacobian information and maybe some uncertainties that we have about our measurements. And in the end, the most computationally demanding task is solving a linear system of the form AX equals to B. And so most of the computational resources are spent on solving this potentially very large system. If we solve this problem, then we have found a new set of parameters that better describes the observations or predicts the observations. If it was a nonlinear problem, we need to iterate this process because we have actually not solved our actual problem, we just have solved a similar problem, and now we kind of have a better initial guess and kind of can repeat this process over and over again so that we hopefully converge to the right solution. What you also need to do in real-world problems, you typically have to deal with outlier measurements. So you will have some observations which are grossly wrong, and you need to take that information into account to not diverge to a wrong solution or diverge into a wrong local minima. And for that, you need techniques such as robust kernels that you can use in order to downweight the effect of these outliers or gross errors, and then focus only on those which appear to be the right ones, but there's in the end no guarantee that you end up in the global minimum. You will end up in a minimum, but not in the global one. And so your initial guess matters. So the better your starting point for the least squares techniques, the better your result will be, because you're more likely to converge into the right minimum and then find the correct solution for your parameters. if you want to implement a solution to a least squares problem that you want to solve on your own, then you don't have to do that from scratch. There are existing solvers out there that you can use which dramatically simplify your life. Some examples are G2O, Ceres, or GTSAM, which you can use, and the only thing that you need to do is basically formulate your problem in the language of that solver. So basically defining your states and defining these observation functions as well as your observations. I hope that was useful and a good starting point for studying least squares. So thank you for your attention. Okay, after we have seen this brief explanation on least squares, let's go very, very quickly over the key points that we had. So we said we have an unknown state, referred to as x. We have some functions f. These are those functions which generate me my predicted measurements or expected observations. And I have my real observations over here. So what I'm looking into is minimizing the discrepancy between what I'm expected to observe and what I observed in reality, and kind of taking the squares of those elements and summing them up. So in the end, I want to vary x or modify x, change x, so that the sum of the squared errors here gets actually minimized. And what I'm doing for this, typically I'm coming up with an error vector, which is exactly the actual observation minus my predicted observations. And again, assuming typically here a zero mean Gaussian noise. And let's say my Gaussian has an information matrix, so the inverse of my covariance matrix indicated over here. Then my squared error can be written in this form of error vector transposed information matrix and the error itself, which gives me my squared error over here. The problem that I have is if this function is linear, everything is fine, but typically this function is nonlinear, or this f contains some nonlinearities. If this is the case, I need to linearize my error function, which, as I said before in this short 5-minute intro, we are typically doing with a Taylor expansion, typically written in the form that my error vector x plus, that's my linearization point, plus some variation from the linearization point delta x is the error evaluated at the linearization point, plus its Jacobian in the linearization point, plus how the delta x, so how far am I actually away from my linearization point. And this matrix J here is my Jacobian, so my matrix consisting of the partial derivatives. Here in every row we have the first dimension of the function, first dimension of the function, first dimension of the function with respect to the first, second, third, nth variable, and down in every row we have the individual dimension of the function. So I have basically the partial derivatives sitting here in this Jacobian. And if I know how the Jacobian looks like, I can compute all the other important quantities over here. And I need to basically compute a matrix H and a matrix B, and then solve Hx equals minus B. And the matrix, the vector B can be generated basically taking a sum over all observations of my error vector, my information matrix, and my Jacobian. And my matrix H is the Jacobian transpose, the information matrix, and the Jacobian. I'm building my matrix H, I'm building my vector B, or B transposed, and then solving Ax equals minus B. And again, here I showed it with an inversion of this matrix H. In practice, we are often not inverting this matrix in order to solve for the best kind of increment or update of my state. Then I can perform the state update and iterate this process if I'm in a nonlinear case and come up with a solution to my nonlinear least squares problem. And this is basically the standard Gauss-Newton approach to do that. Also something that we are going to use from time to time. The next thing I want to briefly look into are skew-symmetric matrices. They are actually quite useful tools, especially in R3, in the Euclidean space, because they allow us to express a cross product of two vectors with a matrix vector multiplication. This actually becomes quite handy from time to time. So from the definition point of view, a skew-symmetric matrix is a matrix S for which holds that the transpose of S equals to minus S. So the transpose should be equal to the negative values of that matrix. And that means already that it must be a matrix where on the diagonal we we have only 0 elements. Otherwise, this wouldn't be a possible. So consider we are in R3 and we have two vectors A and B, and we want to compute the cross product of A and B. So basically, if you have vector A and another vector B, then A times X cross B gives you the vector which is orthogonal on the matrices A and B. And this is, for example, being used if you have two vectors in a plane, you want to compute the normal vector to that plane, or for certain other tasks. Okay, so I can actually write this as a matrix, also written in this form, A and this small x over here times B, or, and this is nothing else in our Skew-symmetric matrix, or Skew-symmetric is S, which is defined based on the vector A, and which has the following form. We have the 0 elements on the main diagonal. These are A and minus A. These are A1. This is A3 and minus A3, minus A2 and A2. So this is the first dimension of this vector A. This is the second dimension of this vector A. And this is the third dimension of this vector A. And if I define my matrix S as in this form, so using the vector A to define this Skew-symmetric matrix, then the product of SA times B is exactly the same as the cross product of the two vectors. So why is it the case? We can very easily show this. If we have A as A1, A2, A3, and B as B1, B2, B3, we compute A times B cross product B, then we have the 3 elements, so just the standard definition of the cross product. But also, if we are starting from this matrix over here and simply executing our matrix vector multiplication, so this, the first row over here times the vector B, second row times vector B, third row times vector B gives me exactly those 3 values over here, so I get exactly the same result. So what I can do with this Skew-symmetric matrix is I can actually express the cross product of two vectors as a vector matrix multiplication. And this is, for example, something that we use in the context of the fundamental matrix or the essential matrix, just to give an example. Those Skew-symmetric matrices are also useful in the context of rotation matrices, especially when it comes to derivatives of rotation matrices or approximations of them, linear approximations. Okay, let's dive a little bit into that and quickly look into how the derivative of a rotation matrix looks like, also some things that we're using from time to time in this course. So just as a reminder, for any rotation matrix that we have, we know that R times R transposed must be the identity matrix. So if I have a rotation matrix and I multiply it with the transpose of itself, then I'm actually not carrying out a rotation. So the transpose of the rotation matrix is actually the inverse of that rotation matrix itself. So consider now, as just an example, we have a rotation by a parameter z theta around the x-axis of a rotation matrix. And I'm writing this as Rx of theta. So this specifies the axis of rotation, and this tells me by how many degrees or radians I'm actually rotating around the x-axis in this case. So just from the definition, we have Rx of theta times Rx transposed of theta must be the identity matrix, because this holds for any rotation matrix, and this is clearly a rotation matrix over here. Okay, so let's start with this expression over here, with this equation over here. And what we can do now is we can compute the derivative of this expression. So computing the derivative of the left-hand side and computing the derivative of the right-hand side with respect to my angle theta, so my rotation angle. So this is the first derivative of this whole expression over here, and this is the first derivative of the identity matrix. First derivative of the identity matrix is equals to zero. So I know that this expression must be equal to 0. And then I can simply expand this expression with the chain rule. So computing the first derivative of the first element times the second element plus compute the first element times the first derivative of the second element. So I have the first derivative with respect to theta of my rotation matrix Rx, and then just multiply R transposed to it. So the first derivative only holds for this rotation matrix, and the same here. First I have the rotation matrix, and then the first derivative of the second part, and this must be equal to 0. Okay? So, and now kind of can exploit the property of matrices, that is the A times B in brackets transposed is B transposed times A transposed. And I can use this now here in the second part of that equation in order to swap the order and so I transpose the individual ones, I'm swapping the order and transposing the matrix itself. So this turns this expression into this expression over here. So no black magic has happened, I'm just exploiting this rule on the transposition of two matrices, is the transposition of the individual matrices and swapping the order. And what turns out to be, actually I have this matrix, a matrix over here, and the transposition of this matrix over here must be equal to 0. Okay? So let's see what that means. So it means S plus, so if we call this matrix S, so we just substitute this by S. So it means that S times S transposed equals to 0. This is S, S sits in here, so S plus S transposed equals to 0. And if I'm just now moving S to the other side by subtracting S from the left and the right-hand side of this equation, this directly leads me to S transposed equals minus S. So this means that this over here is a skew-symmetric matrix. And this is a fact that we can exploit, that this term over here is, the whole term over here is a skew-symmetric matrix. And that can become handy when dealing with rotation matrices. Okay, so let's dive a little bit deeper. So we have here our example that was a rotation matrix around the x-axis. How does a rotation matrix around the x-axis looks like? So the first component here is 1, 0, 0, 0, 0 over here. And we here have our kind of standard 2D rotation matrix sitting in here, cosine, sine, minus cosine, cosine. Okay, so this is this part over here. And if I transpose this matrix, I just need to flip those two signs. So the two signs are flipped here because this is the transpose of the rotation matrix. If I now take this matrix and derive it with respect to theta, then of course constant derived with respect to theta gives 0. 0 stays 0. The cosine turns into the minus sign, sine turns into minus cosine turns into cosine, and cosine turns into minus sine. So this is the first derivative of my rotation matrix over here. And I know now that this product of these two rotation matrices actually is my skew-symmetric matrix that I have over here. Okay, let's see what we can actually do with it. Now let's simply execute this multiplication of those two matrices, right? Of the first derivative of the rotation matrix times the rotation matrix itself. And if I execute this, it turns out that the matrix turns out to be 0 completely, except that I have a minus 1 and a 1 sitting over here. Because the skew-symmetric matrix, those elements must be 0, and then here those elements must be the negative of each other. So 0 minus 0 is the same, so I only maintain here 1 and minus 1. And this is nothing else than generating a skew-symmetric matrix of the unit vector in the direction of my rotation matrix. So if E1 is a unit vector in the x direction, so the vector 1, 0, 0, then the skew-symmetrics of Ex gives me exactly this matrix, which corresponds to the rotation around the x-axis over here. So this was the rotation axis from my the rotation matrix of the matrix I started with, so here around the x-axis. If I would put a y-axis over here, so that the 1 would actually sit in here, and I have the sine and cosine distributed differently, then this would actually give me the same result, except then we have for A2, those elements would be 1 and minus 1. And as a result of this, this would be corresponding to the unit vector EY, which is 0, 1, 0. And the same for the third component as well. So this means nothing else, that this term is the skew-symmetric matrix of the corresponding direction of my rotation matrix. So, and as a result of this, what I can do is I can take this matrix and multiply from the left-hand side, again the rotation matrix R, a rotation around the x-axis with theta. So I'm multiplying here from the left-hand side. Then I have R transposed R sitting over here. It actually goes away. So you can see this basically over here. So I'm just adding the rotation matrix on the right-hand side, so this turns into the identity. And so this is the Skew-symmetric matrix times the rotation matrix itself. And this now is an interesting relationship because it tells us that the first derivative of a rotation matrix is a Skew-symmetric matrix defined through the rotation axis times the rotation matrix itself. And again, this holds not only for the x-axis over here, you can show this for the x and y and that axis, and also for any arbitrary rotation matrix. So in order to compute the first derivative of a rotation matrix, what you can do is you take the direction of the rotation axis, build it in a Skew-symmetric matrix, and multiply it from the left-hand side to your original rotation matrix. So again, this is just a repetition. We can do this for x, y, z, and also for any arbitrary vector r, which defines my rotation matrix. And this, again, can then be used to express an approximation of small rotation matrices. So if a rotation matrix R, which carries out a very small rotation, so it basically means it's an identity matrix, a small extra, plus a small extra. So it's an identity matrix plus some, it's called delta, a tiny rotation that I'm actually executing. And then I can say, okay, this is the same as my identity matrix plus my Skew-symmetric matrix, which is expressed in this case where small variations with respect to the rotation around the x-axis, y-axis, and z-axis over here. So that an infinitively small rotation can actually be expressed through a Skew-symmetric matrix. So I'm taking this matrix and need to add it to the identity matrix and then get an approximation. So it's not exact, it's an approximation of a rotation matrix for small rotations. Again, that's something that can become useful if we look into minimization problems where the parameters inside rotation matrices are involved. So if you want to compute or want to have an error minimization problem where some of the parameters are orientations, this can become a handy approximation for a small rotation. And you can hopefully have seen the direct link between this and these Skew-symmetric matrices. And this brings me actually to the end of this lecture here today. Again, this was very brief and informal, but covered a few topics that we are needing in order to go further in this course. So again, see this as a reminder. If you haven't understood what I was talking about, it may be a good point in time to revisit the textbook of your initial math classes and dive a little bit deeper. So you should know how to solve a linear system ax equals b. You should definitely know how to solve ax equals 0, especially this is something we are using quite often. What's least squares and what's basic Gauss-Newton, something that will also pop up in your life a few times, at least if you stick with us here. Skew-symmetric matrices are handy tools that we use from time to time, and also the derivative of a rotation matrix is something that is likely to pop up the one or the other time. And again, this was the first part of the lecture. In the second lecture, I go a bit more into details talking about homogeneous coordinates as a different representation in a projective space that has some very attractive properties and is frequently used, especially in computer vision and photogrammetry tasks. So it's good to know more about it. So we will do an introductory lecture on that next time so that you also learn things more or less from the basics on. With this, thank you very much for your attention.